Have you ever asked yourself questions about numbers like, why is 0 times 5 0? Well, maybe it's intuitive. 0 of something is none of that thing. Okay. What about why is negative 2 times negative 2 4? More to the point, why is a negative number times a negative number a positive number? Questions like these about properties of our numbers and our number systems lead us to the concept of rings. Appropriately, as we're finishing up our group theory series, I want to just pique your interest in the topic of rings. So today we're going to talk about the ring axioms. Now, just as the discussion of a single binary operation on a set led us to the concept of a group quite naturally, entailing the properties that we want that binary operation to have, so the discussion of two binary operations on a set, which we'll call addition and multiplication, lead us naturally to the concept of a ring. Alright, let R be a ring with operations of addition and multiplication. Then for all elements A, B, C in this ring, the following axioms will be assumed true. First, the associative property of addition. Second, an additive identity element, which we often just write 0 for. Third, additive inverses. Fourth, additive commutativity. Number 5, associativity in multiplication as well. Axioms 6 and 7, the left and right distributive properties. Alright, so these 7 properties together with closure under both binary operations defines a ring. And you'll notice that the first 3 properties together with closure define a group. So R under addition is a group. Moreover, with A4, R is actually an abelian group over addition. So axiom 5 gives us associativity because non-associative structures are really hard to work with, and it also rules out a lot of common things like function composition, which if you followed the series on groups, function composition comes up time and time again as a binary operation. So we don't want to rule things like that out. So we have associativity that is a bare minimum here, and then we have to specify how these two operations can interact with one another, and that is what we have our distributive laws for. And this is what a ring is, bare bones. Alright, so the first thing we want to show is that the additive identity multiplied by any ring element is the additive identity, or in the case of the integers, 0 times any integer is just 0. So the way we're going to accomplish this is as follows. 0 times A is the same as 0 plus 0 times A, since this is the additive identity. And this is by our distributive property the same as 0A plus 0A. Now we're going to add the inverse of this 0A element to both sides, so we'll have 0A plus negative 0A, which we'll call that, is equal to 0A plus 0A plus negative 0A. And of course these are defined to be additive inverses, so this will be 0 and this will be plus 0, 0A plus 0. And of course plus 0 by our axioms once again gives us this, so that we have 0 is equal to 0A. And of course, you can make this argument with 0 on the right instead if you want to do that. Our next theorem. For all elements A, B in our ring, the additive inverse of A times B is the same as A times the additive inverse of B, which is also the same as the additive inverse of just the product AB. Alright, so what we're going to do is take the product AB and add to that negative A times B. And this is going to be equal to, by the reverse of the distributive property, this is going to be the same as A plus negative A times B. This is going to be the same as 0 times b, because, once again, the additive inverse is here. This is going to be equal to 0 by our last theorem, our additive identity rather. And so these two, by definition, must be additive inverses, so that negative a times b is equal to negative ab. And you can make the same exact argument with a times negative b. Alright, so why do two negatives multiply to a positive? It's this simple, straight from the ring axioms. So a times negative b, this being the additive inverse of b, of course, and we're going to add to that negative a times negative b, is going to be equal to, by the distributive property, a plus negative a times negative b. And this is going to be the additive identity, which is equal to 0, right, times negative b, so that this is equal to 0. This means that these two are additive inverses. But we knew before, from our previous theorem, that a times negative b is equal to negative product ab. So this is an additive inverse of this. But that means that the inverse of the inverse, which is just the original product AB, must be equal to this. So we have exactly what we wanted. How do we know this statement holds? What if there are other inverses? What if negative a times negative b has a different inverse? Maybe it has more than one inverse. Well, we learned in our group theory series that this is actually not possible. Inverses in a group, and we know that any ring is an additive abelian group. Inverses in a group are unique, so we know that this is the unique inverse of the negative of this, and thus they are equal. So now you know why two negatives multiply to a positive. It comes straight from the ring axioms. That means it's true for more than just integers. Hopefully I'll be doing more videos on rings soon, so I hope this whets your appetite.